Okay, so in the last lecture, we started with the different configurations of the transistors. We have seen that there are three possible configurations which are possible. One is common base, another is common emitter, and common collector. So in this common base, if we see what are happening to emitter and these different terminals. Okay, let us look at this. So if we look at base, emitter and collector, then in the common base is common to both input and output. In common emitter, it is emitter which is common to both input and output, and in common collector is common to both input and output. In the common base, input is given at emitter. Okay, so we can write here input and output. So input is given at emitter and output is taken at collector. In common emitter, input is at base and output at collector. And in common collector, input is again at base and output is at emitter. So in this way, we have seen that there are three possible configurations as shown over here. And out of this, we can see that output can be taken only at collector or in emitter, whereas input can be given at emitter or base. So now let us look at the some of the common this the characteristics of this common base. So in the common base this common base configuration, we can take either NPN transistor or PNP transistor. So here say we have the any of these transistors. Say this is PNP transistor. Then for the normal operation, we have seen that base emitter junction has to be forward biased, and this collector base junction that has to be reverse biased. So this is PNP transistor. There is no need to write it, but for illustration only, we are writing here. So for reverse biasing this collector base junction, I think it should be clear to all that which terminal is what here. This is base here, collector and emitter. Okay, so between collector base we have this BCB here, and between base emitter we have BBE here. So the base emitter junction is forward biased and collector base junction is reverse biased for the normal operations. So we also have just advocated that input is given at emitter and output is taken at collector side. Okay, and this base is common to both input and output side. Actually these potentials will be just apply here. This is only for biasing purpose. Depending on the biasing voltages, we will have the currents IE, IC and IB, all these currents we can see. We can actually divide the characteristic of the transistor into parts, one related to the input side and one related to the output side. So one that is related to the input side, and that gives the input characteristic, and that which is related to the output side, that gives the output characteristic. So we are just looking here first at the input characteristic. So input characteristic, we can see here that input side voltage is, biasing voltage is BBE. Sometimes this is also called as BEB, because between emitter and base this voltage is applied here. Okay, so sometimes BBE or sometimes BEB, both may be called here. Only the polarity of this voltage may be looked into. Then current, input side current, okay, is entering into the emitter. So the corresponding current is IE. So input characteristic is drawn between IE and BEB. Okay, so for a fixed value of BCB, one can draw a curve here. Okay, by changing the BEB, the current IE is going to change, and because this is just like a forward biased diode. Okay, this is just like a forward biased diode. So the characteristic also looks like a diode characteristic. Okay, after certain cut-in voltage, the current exponentially increases. So for a given BCB, we have a set of characteristic, and for another BCB, we have different set of characteristic. Okay, so we can, by changing BCB, we can have different set of characteristics. Okay, the difference in the characteristic we can see here, that as BCB is increased here in this curve, in this graph here, BCB we can see has been increased from 5 volt to 10 volts. So for a given value of B input voltage BBE, we can see that a higher current is there, okay, corresponding to the high BCB. So that is something which we should look at. So this can be illustrated by qualitatively here like this. So emitter base junction has been forward biased. So this is PNP transistor, and this is reverse biased here, base collector junction. So for a given value of BCB, we will have a certain depletion region to exist at the collector base junction, because this is reverse bias in the normal operations, whereas emitter junction is forward bias. As we increase this BCB, then we will also see an increment or an extension in the depletion width here. Okay, so depletion width will increase. So as BCB increases, the depletion width will also increase at the collector junction. Okay, so because of this, and we have also noted down this, that base is lightly doped as compared to the collector. So most of the depletion region penetrates inside the base. So effective base width, okay, if we look at the effective base width, okay, then this is going to decrease. So effective base bits decreases. Okay, so effective base bit decrease means there is less recombination, less, and so the IB will also decrease, but IC is going to increase. Okay, and uh, for the same biasing voltage here, IE seems to increase actually because of this lower. We can see that base region is decreasing, and so the BC and increase in the current here. Okay, so that's why what happens here that BCB directly is not responsible to control the IE here, but indirectly it affects the IE. So for the same value of BEB, okay, for the same value of BEB, we expect a higher current because of this effect here. So that's why this kind of characteristics we see here. So the input characteristic seems to be a function of BCB as well as IE. Okay. We can say in other words this that for the same IE, if we look at the same IE here, we can put an horizontal line like this here. For the same IE, we require a lower BEB. Okay, we require a lower BEB as compared to the uh, higher value for the low BCB. Okay, if BCB is low, then we require a higher value of BEB, whereas if BCB is large, then we require a lower BEB for the same high current. So input voltage BEB seems to be a function of BCB and IE here. Also one can say that IE is function of BCB and BEB. That may be also true here. But in diode, the current, okay, the current is said to be independent variable. Okay, that's why this relation is written over here. And the dynamic resistance offered in for the forward bias emitter junction can be written as change in input voltage divided by change in the input current at a given BCB. Okay, so the same thing is illustrated over here that depletion region width is increased when this BCB has been increased from 5 volts to 10 volts, and because of this is happening. So the region is like this here that due to reduction of electrical base width, gradient of charge concentration increases, which causes more diffusion of carriers emitted from emitter. Okay, that's why this is increased. This fact can be illustrated graphically like this here. In the next slide, we have, I think, this graph also here. Okay, so the charge carriers which are injected from emitter into base some of these recombine the base and rest they are collected by the collector. So say when we have the for a given BCB, say depletion region starts from here, then we have the slope, okay, of the minority charge carrier concentration like this, which governs the diffusion, okay, diffusion of these charge carriers. So minority charge carriers, they diffuse through the base region and reach eventually to the collector. We have already seen that at collector, the concentration of this minority charge carrier goes down to zero because all carriers are swept across the depletion region and collected by collector. If we have a higher BCB, then this depletion region penetrates more inside this base here, and so the effective base width is decreasing here, but depletion region is increased here. So we have a higher slope here, as we can see. We have a higher slope for large reverse bias. So the diffusion current increases. Okay, so that's why the current IE seems to increase here. For the same value of BEB, the current IE seems to increase. Okay, so this is the effective base width. WB is the physical base width minus W. This is the depletion width. Penetration, depletion, penetration into the base. Now we can look at the output characteristics here. Output characteristic is given for the output side of this common base configuration. So in the output side, we have the collector base voltage between this collector base voltage BCB and the current IC. But this IC does depend on the input current IE as well, okay? Because a fraction of IE is collected by collector to form the collector current IC. Of course, this can also be changed with the BCB, as already we have seen that effective base width is going to decrease. So that is also going to affect the IC. So in this way, we see that IC current is dependent on the BCB and IE. Okay, so we can choose different values of BCB. Here in this graph, if we put the BCB values such that it always reverse biases in the collector base junction, then we are in the region shown by the white region here, which we call as active region, this region. Whereas if both junctions are off, okay, if base emitter junction is also is off, and this is also off, okay, by suitable reverse biasing voltage, then we are in the cutoff region. Okay, so in the cutoff region, there is IE is equal to 0. Okay, this IE is equal to 0. There is no emitter current. It will appear as if this is not connected. Okay, open circuited. Emitter is open circuited. So IE is equal to 0. In this case, we have seen that ICO current flows. Okay, which comprises of two current components, INCO and IPCO. Already we have seen. So these currents may still flow through the collector, and that's why we have a non-zero collector current IC. For the case when IE is equal to 0, that is when the emitter junction and the collector junction both are off. In that case, we still have a current IE, IC. Okay, so this is the shaded region under this curve. IE is equal to 0. This is showing the cutoff region. If we apply such a voltage across the collector base, which makes this on actually, okay, that is both junctions JE and JC, the emitter junction and collector junction, both are say on, that is forward biased. If this is both are forward biased, then we see a current as the IE changes, the IC also changes quickly, but we don't see a large current in under such a situation. Why it is so? Because we see that let us look at this diagram here for more clarity. So now suppose for this PNP transistor, both are forward bias. Forward bias means one is applying this voltage, one is applying this voltage also across this. So through this the current will try to flow from, okay, at emitter junction like this here. At collector junction the current will try to flow like this. So what looks like that both emitter current and collector current are opposing to each other. But we see that emitter current will be large as compared to the collector current. Why it is so? Because emitter is heavily doped, whereas collector is lightly doped as compared to the emitter. Okay, so because of this, we will see a difference in the currents here, and there will be current which is going to change exponentially, of course, as the BBE and BCB are getting changed here. So is the current. So there is a huge change in the current with change in the small voltage here across BCB. Suppose for a given BBE, suppose we fix the BBE and change BCB, then we will see a huge change. So we can see that the current is going to increase as we increase BCB in the reverse biasing direction, that is from a negative value to 0 here. So negative voltage means opposite polarity of the voltage source as shown in the here. So reverse bias voltage means the polarity of the voltage here is going to change here. So this reverse bias voltage is being called as a positive voltage, and the forward bias voltage is being called as a negative voltage. Okay, that's what the convention is over here. So as BCB is increasing, that is from minus somewhere 0.8 to 0, then we can see that the current is increasing very quickly and reach to a value which almost is very large. Okay. But as BCB is increased further, then we have a current as shown by this. So as BCB will be increased, then a more value of IC means carriers are being collected, will be collected by the collector. Okay, so collector current should increase. So here we have, based on the these emitter junction and collector junction, how they are biased. So active region, inactive region, emitter junction will be forward biased and collector junction will be reverse biased. In the cutoff region, both are reverse biased. Whereas in saturation region, both are forward biased. So below table summarizes the different states of the emitter base and collector base junctions. We can define some preliminary uh, parameters like current gain. In the common base, we can see that IC is equal to alpha times IE along with some ICO, okay, plus ICO. ICO is for the most of the cases very small and neglected. Here an alpha is very close to unity, so sometimes this is of course very crude approximation, but sometimes it is written like this, that IC is almost equal to IE. Base emitter voltage for silicon, okay, for silicon transistor, this is valid for silicon transistor. BB is 0.7 volt. 0.7 is similar to this silicon diodes, okay, in which the forward bias, okay, for forward biasing, at least we have to apply a voltage 0.7 volt. So that is the minimum voltage. Once this is for bias to 0.7 volt, we applied have a huge change in the output current. Sorry, this emitter current here. So from input characteristic, this can be revealed here that for silicon transistors we require at least 0.7. This voltage actually appears across this emitter junction. Just like a forward bias diode has a voltage across it equal to the cut-in voltage or the potential barrier. The same thing happens also with this. Common base current gain can be defined here to be alpha approximately given by IC upon IE. So ideally we should have alpha to be equal to 1, but practically we have this value between 0.9 to 0.998. We can define again another term called as output resistance. Output resistance can be defined as change in the output voltage VCB to change in the output current for a given IE. Okay, so this situation shows only here that when emitter is open, then what is the value of the current flowing through the collector. So through the collector, the current which IC flows is called as ICBO. This has nomenclature like this here. O is standing here for emitter open and CB is for collector base junction. Okay. So the current which flows between collector base junction when emitter is open, that one is calling as ICBO, and this is nothing but the called as a leakage current. Okay. Because this current keeps on flowing even though we don't apply any IE. So IE, input current, which is regarded as, that is 0. So still we can write the current equation. IE is equal to IC plus IB. It is always true here. And IC is equal to alpha times IE for common base. So these are the things which we define. So this IC is equal to alpha I. This is approximated value as already discussed here. Along with this uh, this along with this alpha IE, we also have this leakage current ICVO which flows. Okay, this is nothing but ICO which we have been discussing. One more thing it is interesting to look at is punch through effect. So we have seen here that as we increase BCB, then the depletion region, okay, the depletion region from the at the collector junction, okay, this increases as we increase BCB, but collector is heavily doped as compared to the base, so more penetration is inside the base. So as one increases BCB, then there may be little increase in the depletion region inside the collector as compared to that happens in the base. So one keeps on say increasing this, then what may happen that base, okay, this depletion region extends inside the base to such a extent so that this just start touching the interjunction. Okay. So in this case, what happens here that base region is going to extend. Okay, base region extends. Okay, so because of this, the transistor action fails. Okay, so whatever is the carriers being injected from emitter, that will go into the collector, right, like this here. Okay, and of course actually BCB, in the meantime BCB may be such a large value, okay, which may lead to very large electric fields. Okay, so as in the diodes we have seen that a large electric field may be a cause of general breakdown kind of thing, or other or avalanche breakdown kind of things may be activated. Okay, under such a situation, and this is not going to be healthy for the transistor. This particular condition is called as punch through or reach through. Okay, so mostly it is recommended that we should operate our device well below this maximum BCB or the punch through voltage. Okay, so we limit our operations well below this BCB max, else we may land up into the breakdown region, and that may not cause damage at the first sight, but if we um, try to operate multiple times the device in such a in this breakdown region, then it may damage the device itself. Okay, so that's why we should limit our operations below this BCV max. This is mostly given by the manufacturers. Okay. Transistor amplifier already we have seen in the last lecture. I think I placed this here slide. Before proceeding here, let us look at quantitative example here, which gives a feeling what kind of gain we may be achieving out of this. What seems here that the input current, which is for us for the common base, is IE and output current is IC here. Okay, we have seen that IC is almost equal to IE because alpha is almost equal to 1. So, and the input side is a forward bias, this emitter base junction, and collector base junction is reverse biased. Okay, so reverse bias gives a high impedance, and the forward bias gives a low impedance. So we are able to here transfer the current IE, which is we are able to transfer this IC, which is almost equal to IE, means same amount of current over different resistances, okay, from low to high. So this gives a kind of amplification here in terms of voltage gain. Of course, if we look at the ratio of IC upon IE, which is nothing but alpha, and this is almost 1, or most of times less than 1, typically 0.9 to 0.998. Okay, that typical values we have seen here. So alpha seems to be not that much great. The current gain, this we may call this as a current gain. Current gain is not that much great, but if you look at the voltage gain, then it is good number. So that can be explained here by calculating the input current IE, which is depending on the input voltage and input resistance, because this is forward biased here emitter junction. The corresponding forward bias resistance is low, 20 ohms here given. So the peak value of the emitter current, okay, this is the peak values. 200 millivolts is the peak value, okay, plus minus 200. So this is peak value. So peak value of the current is this much. The output current peak value is also this much, and output voltage, that matters here. The same current multiply by this 5 kilo ohm, that gives here 50 volt. Okay, so if we look at the ratio here, output voltage, the input voltage, then it is 250. So that's how this gives a amplification here. Okay, so typically we gain in terms of the voltage by the common base configuration. Okay, so this can be used as voltage amplifier. Another configuration now we can see here is a common emitter. The common emitter, the emitter terminal is kept common to both sides here. This is input side, this is output side here. The input current is given as the base here, input voltage and input current between base and emitter, and output is taken between collector and emitter. In transistor view here, this is symbolic view, this is a transistor view. Actually, if we look at this transistor circuit, so this is PNP transistor. Okay, this is PNP illustration, and this is NPN illustration here. So in the PNP here, the actual current will flow like this here. Whereas in NPN transistor, the actual current is flowing like this here. So in this case also, the voltage VBE can be set to be a function of the BCE and IB input. Similarly, IC can be set to be a function of BCE and IB here. So this gives input characteristic here, and this gives us the output characteristic here. So input characteristic is drawn between base, the input current and input voltage. So as seen earlier, the input voltage is IB, and here it is BB, but it is this also is called BBE because this is applied between base and emitter. And here it is BCC, but most of the times this is also called as BCE because this is applied between collector and emitter, and the current is here IC. So it is between IC and BC, the output characteristic, and the input characteristic is between IB and BBE for different other parameters, whether they are constant or varying. So if BCE is small, BCE is giving us the reverse bias here, okay, across collector emitter. So BCE is the voltage applied between collector and emitter. If that is small, then we have a large current. This can be just seen by just placing a line here. So for the same BBE, we have a higher current. Okay. So we have a higher current, whereas if this BC is increased here, then the current is decreased here. So let us call this as 1, 2, and 3. Okay, so BCE 1, 2, 3. Okay, so why it is so? IB1 is greater than IB2 is greater than IB3. This can be just understood again here by looking at the cross-sectional view of this transistor. We can take any transistor, PNP transistor or NPN transistor, and let us apply some voltage between base emitter here, and for forward biasing this base emitter junction. And another thing here is done now between collector and emitter. So we apply another voltage here between collector emitter. Okay, so if collector emitter is voltage is less here, then we are actually putting a less bias, reverse biasing voltage across this. What is the effective voltage between this collector junction, across collector junction? We have seen that we can write BCE is equal to BCB plus BBE, okay, like this. So BCB effectively can be written as BCE to be equal minus BCE minus BBE. Okay. So effective collector based bias voltage will be BCE minus BBE by this. So higher the BCE value, higher the reverse biasing voltage. So higher the reverse biasing voltage means the more depletion region will be there across the collector junction, and we will see a less recombination. Okay, in this will be the effective base width now. So less recombination and hence less base current. Whereas if the base region is large, then there will be more recombination, more injection of the charge carriers from here emitter into from base into emitter as well. And also one more thing that we have seen, that the slope, okay, slope is also going to be low. So if low slope is there, then IC is less and IB is going to be more. We can look at this transistor equation. I is equal to IC plus IB. So if IC is less, then IB is going to be more because it is IE which is being fixed. So because of this reason, we see that IB, okay, this at the reverse bias voltage BC is increased here, then the base current is going to decrease. That means the collector current is increasing. So if there are certain comments here, if collector is shorted to emitter, that is BCE is equal to 0, and emitter junction is forward bias, then input characteristic is same as that of the forward bias diode. There is no difference in that case. Whereas if BB is equal to 0 and IB is equal, then what will be happening? IB will be equal to 0. Since under this situation, both emitter and collector junctions are short circuited, so there will be no base current if BB is equal to 0 and BC is also 0. Whereas increasing BC with constant BB causes a decrease in base width and results a decrease base current. Okay, that we discussed just now. The output characteristics can also be seen here, which is a function of uh, output voltage BCE and base current IB. These two graphs shows here, one is for a typical NPN transistor and another is for the PNP transistor. So again we do see three regions here: active region, cutoff region and saturation region. So if IB is 0, okay, and for IB is 0, we increase BCE, then we don't see much current here. This region is called as cutoff region. So IB0 means that base emitter junction is reverse biased kind of thing, and BC increase, that is also reverse bias. So both junctions are reverse bias, and BC only leakage current. The leakage current is now ICEO. O stands here for base open, and CE stands for the current between collector and emitter junction. So ICEO is similar, a current value which is similar to ICBO of the common base. Okay, in the common base we have called this ICBO, and here in common emitter we call this leakage current as ICEO. Whereas when both junctions are forward biased, then we see again a huge change in the current in this situation. And one more thing here, we can see that as IB is changed here, different values, then the current IC increases rapidly as IB increases. Okay. So this active region, in this active region, as earlier advocated, that emitter junction is forward biased and collector junction is reverse biased. So IB is actually very small as compared to IE. If we look at IB is in microamperes order, whereas IE or IC is of the milliampere order. So the difference in the common base and common emitter is that slopes are larger than in common base. So slopes we can see is more here in common emitter as compared to that in the common base. So in the active region is of utmost importance here. So right of ordinate BCE, which for few tens of a volt above IB0. So IB0 we have seen in the previous case here, IB0 above this IB0, and right side to this BCE set. Okay, so this is the region of which is called as active region. So for amplifying actions, we will also consider this point in much detail later, that for amplifying actions, transistor is used in active region, in this region. We can work with some set of equations here to generate some relations for the common emitter configuration here. So from transistor equation, IE is equal to IC plus IB. And this is due to the KCL. And this equation is the transistor current equation. IC is equal to ICO minus alpha IE. IE here is replaced by this KCL equation, rewritten in this form here. Some adjustments are done here, and equations like this we can have now. And from this equation, IC can be written like this here. Why this is done here? In the common emitter, we see here that our current input current is IB and IC is the output current. Okay. Whereas the transistor equation here, which we have IC is equal to ICO minus alpha IE, it doesn't directly relates with the IB here. So to relate this IC with IB, we do this mathematical operation here, and from here we define a coefficient alpha upon 1 minus alpha to be as beta, and 1 upon 1 minus alpha, which we can see in the first term, this can be written 1 plus beta as 1 plus beta. Okay. So the above equation IC is equal to this equation ICO upon 1 minus alpha can be written as 1 plus beta ICO plus beta IB. And this is what? Okay, this is what 1 plus beta ICO is called as ICO. So for common emitter, we rewrite this equation as IC is equal to beta IB plus ICO. Or sometimes it is just written as ICO, but that is wrong. That doesn't gives much insight. Okay, so better to write ICO for common emitter configuration. IB is actually larger than this ICEO. It should be ICEO. So IC is almost equal to beta IB. Okay, with this we can stop here. We can continue from here in the next lecture because time is over almost. So we stop here. We shall continue from here in the next lecture. You can on your own in the meantime try to do this mathematics on your own. Okay, this is very simple one, but if you do on your own, this may give you more insight. Okay, thank you. With this we stop here. If you have any questions, you can ask.